Okay, in this video we're going to take a look at marginal and conditional probabilities. So they're often dealt with together because they usually kind of apply to the same type of scenarios. So marginal probabilities, they're named because they appear on the margins of a probability table. And a conditional probability is the probability of an event occurring given that another event has already occurred. So we're setting conditions on our probability. So probably best explained by an example. So 100 employees of a company were asked if they were in favour of a flexi-time work scheme being introduced, and the results are shown below. Okay, against there was 45 males, 36 females, and for there was 15 males and 4 females in favour of this proposal. So when the data is presented like this, it's difficult to tease out, details of what's the probability person selected at random is a male, given that they're against the proposal. These are the kind of questions we want to ask. But when the data is presented just in this raw form, it's very difficult to draw out the details that we want. So our first step is we can produce the data in what's called a two-way table, as below. And now we can start to extrapolate even more data from this, because this is where the margins come in. As we start to add across the margins, well, there's 81 people against the proposal and there's 19 for the proposal. Then if we add along the bottom, well, there's 60 males and there's 40 females. When we add these will add to 100, and when we add these will add to 100. So the key is this value here adds to 100. So these are now called the marginal probabilities because they weren't given in the question, but we can extrapolate them from our data. So it looks a bit neater on the next slide. And here's all our information. And all this data here is new in a way. This wasn't given in the question, but we've developed it from the information we've been given. And these are called your marginal probabilities. Once we write them over, obviously, the total amount, which is a nice easy number in this case, 100. So now we can say, well, the probability of person selected at random is a male is 0.6, female 0.4. Probability a random selected person is against the changes, 0.81, and for the changes for 19. So none of these were given in the original piece of information, but we've developed them just by extrapolating the data we had originally. So these are our marginal probabilities. In questions and all, you'll be given the kind of raw data and you'll be expected then to draw the table and then develop the marginal probabilities yourselves. Now we'll take a look at conditional probabilities. And this is the probability of an event occurring, as I said, given that another event has already occurred. And it's written with this context PA, and there's a straight line. It's longer, it's considerably longer than the length of the capitals. And the condition always sits at the end. This is the condition. What's the probability of A given that B has occurred? And this we have given the probability. This is the same but just written another way. Probability of B given that A has occurred. So we can use a formula like this. This is the formula for it. This is our and or not rules working. Or we can draw a probability tree, which we'll look at later. So we'll use the formula first and then we'll draw a probability tree, and we'll see that the same information can be teased out from the probability tree. So just to discuss the formula, this is the probability of A and B both happening. Remember, we multiply those probabilities. And then this is the condition. So the question will usually tell you what the condition is, and that's what you're going to be dividing by. Divide by that probability. So again, best explained by example. So if an employee who is a male, so that's the condition, is selected at random, what's the probability that he's in favor of the flexi-time scheme? So when we have our condition, there's the condition. So in this case, it would be written as probability of, so we're interested in that they're in favor, given that the person is male. So now what we're looking for, when we feed these into the formula, remember it's the probability of being in favor and male. And we can find that from the table, how many males were in favor. And then the probability of being male. Have it a bit more neater. Oh. And now on the next slide, I just use the formula. So this is both. Very important to remember what goes where. This is the condition. So we can see there was 15 males who were in favor of the proposition over a total of 60 males altogether. Note how the condition is in there. We're not dividing by 100. And when we work this out, we get the probability of a person selected being in favor, given that they're male, is 0.25, or 25% if we wanted to talk about relative probability. Now we're asked to determine the conditional probability that a randomly selected employee was female. What's the probability that a randomly selected employee is female, given that this employee was in favor of the flexi-time scheme? So note now, being in favor of the scheme is the condition. And then we're asking what's the probability of a person from this group, the in favor group, being female. Remember, both on top. In this case, I think there was four ladies who were in favor of the scheme. The total number of people in favor was 19. And that gives us this probability. We can work this out to a decimal. Sorry, I don't think I've done that. So this gives us 0.2105. And it goes on for a bit. Now, alternatively, we could use a probability tree. Bit more detailed, a probability tree, but the great thing about a probability tree is everything is laid out in front of you. But the order in which you write the probability tree depends on the conditions been asked. So we'll take a look at both the previous questions. Probability of this one, using a probability tree. And then we'll take a look at this one, using a probability tree. So first one was the probability that, given the person was male, what's the probability that they were in favor? So male, the condition is first when we write a probability tree. Note these will add to 100, the total amount. So each branch, when you add the branches of the probability tree, it must equal the total. So here we have all the people taken care of, 60 males, 40 females. So that's the first branch of our tree. And now we branch again in terms of, well, are the males in favor or against? Do the same for the females, in favour or against. And now we can say, well, what's the probability of a person selected at random is against the proposal given that they're male? There's our condition, that's what goes on the bottom, and 45 goes on top. What's the probability that they're in favour of the proposal given that they're male? 15 on top, 60 on the bottom. This is the one we just found. We can do the same for the females, probability of a person being against the proposal given that they're female. And you can see then, we can see that a lot more females, a greater percentage of females were against the proposal than men were. So this is one of the great things about a probability tree. It kind of allows even more detail to be drawn out. So remember, guys, we've got all this information now just from those 4 little bits of data, that we had 36 ladies, 45 men, 4 ladies were against, 15 men. Sorry, 4 ladies were for the proposal and 15 men were for the proposal. So just from that very raw data, we're now suddenly developing, you know, good solid information about this cohort of people. So in terms of the first question, this is who we were interested in. What's the person of a randomly selected person being in favour of the proposal given that they're male? It's a little bit of a mouthful, but there we have our 25% or our 0.25. And there's the answer we're interested in. I've circled it. Just note as well that our probabilities then, these two add to 1, because it includes all the females are included in there. Those 2 probabilities add to 1, as do these probabilities add to 1. So a probability tree is quite complicated in a way, but it offers up a huge amount of information. We can see that the number of females who are against the proposal is considerably greater than the number of males. So this is why, from quite a limited amount of information at the start of the question, we can now develop quite a rich picture of this particular cohort of people. Now in the next slide I'm going to draw a probability tree again, but this time we're looking at the second question we were asked, where what's the probability a person selected at random was female given that they were in favour of the proposal. So again, the condition is always the first leg of our probability tree. And now the next leg, we're going to break it up into the sexes. So of the 19 in favour, 15 were male, 4 were female. And of the 81 against, 45 were male and 36 were female. And once we've laid out the tree, now we can start to tease out all the details. What's the probability that a randomly selected person was male given that they were in favour? It's going to be 15 over 19. Female, given they were in favour, 4 over 19. What's the probability the person is male given they were against? And female, given that they were against. Note again, these add to 1 and these add to 1. We've covered all possible probabilities, is what I'm saying when I say they add to 1. There's nothing, there's no people left out. The probability tree encompasses the totality of information. So the question we were interested in was this one. We worked it out just using the formula earlier, and this is just to show you how we can work it out using a probability tree. As I said though, the probability tree allows us to start comparing between the different groups. So there's an awful lot of information. There's an awful lot of rich information from a probability tree that just wouldn't be available from the data as we saw it at the start of the question. So now we're going to take a look at another example. We won't do probability trees on this one. I will do them on later slides again. But here we have some data about a group of students who attended a party, and there was a barbecue at the party. Some people got sick, some people didn't get sick. So a student is selected at random from this group. Determine the probability that this student ate barbecue, was not sick, ate barbecue given they were not sick, or did not eat barbecue given that they were sick. So we look at each of these in turn. Sounds a little bit, again, probability always sounds confusing anyway, so we'll take a look. First we're going to do though is fill in the marginal values, and now we can start to answer the questions. So what's the probability that a student ate the barbecue? Well, how many of them at the barbecue? There's 120 out of 200. So there's no conditions or anything. We're simply looking at marginal probabilities here. What's the probability a student at the barbecue? Well, 120 out of 200, 60 over 100. So 0.6. I'll wrote those. What's the probability that a randomly selected student was not sick? Well, how many were not sick? There was 90 out of 200, so that's 45 over 100. Divide top and bottom by 2. So 45% probability that a randomly selected student was not sick. But now we start... Oh, I can't get rid of them. Sorry, that was 0.6. I didn't mean to wipe those, sorry. What's the probability a randomly selected student ate the barbecue given that they were not sick? So remember, the condition goes on the bottom. So how many people were not sick? There was 90. Then we're asking how many people were both that they ate the barbecue and were not sick. That's 30. So this gives us 0.333. 1/3. And now the final question. Did not eat the barbecue given that they were sick. So now being sick is the condition. So there's 110 students who were sick. And how many did not eat the barbecue? 20 of those did not eat the barbecue. So when we work that out, we get 0.1818. Watch out for the repeating decimal. So on my calculator, just to highlight this, on my calculator the answer just appears like this. And on the Casios, those little dots can be very small, but they're vital because they're telling us that both of these are repeating decimals. So it goes on forever. So just using the formula can be quite simple, as I was saying, but the probability tree gives you that big rich picture of what's going on as well. We'll take a look at just genetics. This refers back to the first lecture when we were talking about the attached and detached earlobes. Now we're just talking about a disease-causing mutation. It's recessive, little d. So if both parents carry one copy of a recessive and then one copy of a dominant, so both parents would have this kind of a allele pairing. So these are the possible outcomes. That the child is not a carrier. It's got both the dominant genes, the non-disease carrying gene. And when we start to work them out, if we did the little table, remember, DD, this is the father, the mother, D and D, and when we draw a little table, these are all the outcomes, DD, sorry, it's going to just be DD. And this is the recessive one. So this child, unfortunately, would have the disease. The child is not a carrier. And then the child is a carrier but doesn't have the disease, but they can pass on that recessive gene to further generations. When we work these out, the probability of the child not being a carrier is 1/4. Probability the child is a carrier but doesn't have the disease. There's 2 of these, this one and this one. So that's a 50%. And then third one, probability that the child has the disease is 0.25. So it's very similar to the one we looked at with attached and detached earlobes. But we can draw a probability tree. And here we have the mum's allele. So equal likelihood, 50% chance of the dominant or the recessive gene being passed on. And then we have the father's allele. Again, equal chance that either dominant or recessive can be passed on. And then when we take a look, the child's outcome, on the top, it's just DD. Sorry, capital D, capital D. The next, this one is P, DD. Next one is small d, big D. And the last child then is the unfortunate one who gets both recessive genes and will have the disease. So this just answers the question then. How many will be carriers if we wanted? 50%. 50% chance a child would be a carrier. 25% chance the child would not be a carrier and free of disease. And a 25% chance that the child would be unfortunate and have the disease. Adds up to a total of 1. So all probabilities are accounted for here. Now we take a look. This is regular exam problem, HIV or some other disease. So probably do one with COVID for your journals this year, considering it's the mot de jour, as they say in France. So if HIV is a prevalence of 3% in San Francisco, and a particular HIV test has a false positive rate of 0.001 and a false negative rate of 0.01. First of all, just to explain what a false positive is you probably know about them now with COVID tests and stuff, but a false positive happens where a person who is tested, they don't have the disease. That's a condition, that they don't have the disease, but the test tells them that they do. So it's obviously very upsetting for a person to receive a false positive, but on future testing it will come out that they actually don't have the disease and that the first result was. So even though it's very upsetting for the client, for the patient, it usually has a good outcome because ultimately they don't have the condition. A false negative is much worse because here a person who has the condition, they take the test and the test tells them that they don't have the condition, and obviously the ramifications of that are very serious. This person could continue to infect other people unaware that they're infected themselves. They're not being offered treatment for their condition. So a false negative they're both bad, but a false negative is a much worse outcome ultimately, both from spreading a condition and not treating somebody who has a condition. They're both, they're both bad. So we're going to ask these questions here. What's the probability that a random person selected off the street will have HIV and test positive, not have HIV and tests positive, tests negative for HIV, has HIV given that they tested negative? So we have to explore all of these. And the best way to do that in this case is to draw a probability tree. Now be careful as well with the 3%. We need to convert that into a decimal. So on the top we have the people who have HIV, and on the bottom we have the people who don't. Note how both legs still add to 100%. We're encompassing the totality of information in our probability tree. And now we're going to take a look at the test. So if somebody has the disease, the only thing that will affect them is a false negative. If you have the disease, you're not going to get a false positive. It's going to be a true positive. So here's the false negative rate. So we're only told the false negative rate. They test negative, even though they have the disease. I'll just write it in this once. And obviously then 99% of people will test positive who have the condition. When we look at the people who don't have the disease, well, the only thing that will affect them is a false positive, because they would be told incorrectly that they do have the condition. So here's the false positive here. Again, that's given in the question. So this then are all the people who don't have the condition and test negative. So this is the majority of tests here. And now in this case, we're really saying and between each leg. So what's the probability somebody has HIV and tests positive? We multiply both of these values. What's the probability somebody has HIV and tests negative? We multiply these two values. I hope this makes sense. What's the probability somebody doesn't have the disease and tests positive? We multiply those two values. And finally then, what's the probability somebody doesn't have the disease and tests negative? We can see that's the vast majority of people. When we add all these values together, we will get a total of 1. So now we're in a position we can start to answer the questions. So I'll just draw out the probability tree again. And now the question, what's the probability that somebody, that comes in at the wrong time, has HIV and tests positive? It's this group up at the top. Now we can just take that probability. Here's the tree again. Now the question, it comes up before the question, does not have HIV and tests positive. Does not have HIV and tests positive. That's the probability there, that a randomly selected person would not have HIV but tests positive. Question 3. So once you have the probability tree, it can be quite easy to pull the answers out because all the information is there. You just have to kind of really identify it. What's the probability somebody tests negative? Well, there's two groups test negative. It's these guys and the people with the false negative. So we just add those because this group or this group both test negative. So remember, the word or means we add our probabilities. And finally then the conditional probability is, now we'll use this figure again in the next question because the condition in the next question is that the person tests negative. So we'll be using this as our divisor when we're answering the final question, because this is the probability that somebody tests negative. Just set everything up. So the question then, what's the probability that they have HIV given that they tested negative? Well, this group here has HIV and they test negative. So this is the both condition. Remember, it was probability of B and A both over the probability of A. So when we work this out, this was the value from the previous slide, the condition that they both test negative. This is the condition, and then this is the people who are both HIV positive and testing negative. Remember though, because of a conditional probability, we divide. So it's very important to understand, when do I multiply? With the word and. When do I add? With the word or. When do I divide? With the word given. Or, you know, the context of the question would suggest a condition. It mightn't always be with the words given that. So that answers that one. That's kind of all our questions answered. But you can see, now you don't need to draw a probability tree each time you want to answer each part of the question. I just felt it was clearer, rather than the slides would have got quite crammed if I tried to include all 4 questions on the one slide. So usually you would just draw one probability tree and then answer all the questions from that. So now we're just going to look at another way of answering probability questions, and this is using Venn diagrams. So 100 employees have been examined. 42 employees have gained promotion within the last 8 years out of a company. 60 of the employees have a 3rd level qualification, and 35 of those with a 3rd level qualification have gained promotion within the last 8 years. If an applicant is selected at random, what is the probability she does not, or he, they would be a better word there, just to be. What's the probability they do not have a 3rd level qualification and has not gained promotion? Has a 3rd level qualification or has gained promotion within the last 8 years? Does not have a 3rd level qualification or has not gained promotion within the last 8 years. So this question 3 sounds a lot like question 1, but there's very subtle differences because of that word or. So the best way to go about this is to draw actually a Venn diagram, because we have this overlap, people who are overlapping both of the conditions. So we'll just take a look. You'll probably remember Venn diagrams. So we have 3rd level and promotion. Now always start with the overlap first. There's 35 people have both. Now 60 people had a 3rd level qualification. We've accounted for 35 of those. So now in the 3rd level circle there's 60 people. Of the people who gained, there was 42 people who gained promotion in the last 8 years. 35 of those had a 3rd level qualification. But we're missing something. This doesn't encompass all the people, so we have to seal off our sample space and kind of include everyone. There's 33 people who don't have a 3rd level qualification and were not promoted in the last 8 years. And that's actually the answer to the first question, I'm pretty sure. So it's just simply 33 people. If we're asked to do it as a probability, there was 100 people in the company or 100 people sampled. So no 3rd level and no promotion. So it essentially means these people are excluded. So 33 were left. How many people has a third level qualification or has gained promotion with the last 8 years? Well, how many people have a third level qualification? 60. How many people have gained promotion? 42. But, so it's really 60 plus 42, but these 35 are being counted twice. So when we work that out, we end up with 67 people. The last question then, this is the one that causes the most confusion, does not have a third level qualification or has not gained promotion within the last 8 years. So we look at the first one. How many people do not have a third level qualification? Well, that's these guys here. So that's 40. How many people have not gained promotion within the last 8 years? These guys weren't promoted and these guys weren't promoted. So that's 58. But as before, these guys, the 33 people, are being counted twice. So we need to subtract them. So when we answer the third question, we get a probability of 65%. So that brings us to the end of this lecture and brings us thankfully to the end of probability. And so thanks for bearing with me, folks. We'll leave probability there and we'll chat to you again for the next lecture, which will be on normal distribution.